All right, hello everyone. So we're back on the handout. I am on the top of page 10. And so we're coming from using StatKey. We were able to at least see that for this sampling distribution, if we increase our sample size, then the distribution kind of slowly becomes more normally shaped. So for a sampling distribution for our sample size of 11, we saw that that was a little bit skewed, but we settled on our sample size of 32 for that particular example, and when the sample size was that high, we saw that the distribution was approximately normal. Instead of always using StatKey and kind of making these kind of subjective judgments that might vary between person to person, we do have kind of a rule of thumb for how large the sample size should be for the sampling distribution to be approximately normal. Our rule of thumb is that n times p should be bigger than or equal to 10, and n times 1 minus p should be bigger than or equal to 10. If both of these hold, then the distribution is approximately normal. In addition to this success-failure condition, the observations that we're dealing with should also be independent in order for in order for the sampling distribution to be approximately normal. And so this is kind of condition number one. This is condition number two. And independence, we're going to have a few different kind of rules of thumb for when independence holds. One of them is if we have random assignment in experiments. Another is if we have a simple random sample, then it usually holds in this in these types of settings as well. And then we're just going to make a note that if we're sampling from, or if sampling is from a different process, like a convenience sample, for example, then we need to use some logical reasoning. So this is important, this checking independence. We are mostly going to ignore it for now, just because it's something else that's new, and I think we kind of have enough to think about right now. But it is very important, and we will come back to it. So for now, we're just going to assume that it always holds, and I'm just going to write more on that later. All right, so again, independence, it is super important. We will talk about it, but there's kind of enough new stuff with all this sampling distribution and success-failure condition and all that. All right, and so this is the central limit theorem just says that if these two things hold, so if the success-failure condition holds and our observations are independent, then the shape of our sampling distribution is going to be normally distributed. The mean of our sampling distribution is always p, which is the usually unknown population proportion. All right, so we saw that in StatKey because we saw that the distribution was centered around 0.68, which was our population proportion. And it even gave us the mean as being like 0.676 or 0.68 or something close. The standard deviation of the sampling distribution is not as intuitive. It's p times 1 minus p divided by n, and the square root of all of that. So remember, n is our sample size, and p was our population proportion. We won't derive this because it's not theoretical stats, this is applied stats, but we will kind of reason through it in a sec. So like if you kind of remember that when we upped the sample size, then the standard deviation of our sampling distribution got smaller. So when we changed from 11 to 32, it like decreased from like 0.14 to about 0.08. We could see that from this formula. Since we're dividing by the sample size, then a sampling distribution for a larger sample size is going to have a smaller standard deviation. So we could at least reason through it a little bit that way. We could check, remember we had settled on n being 32. We could check to see if it satisfies our success-failure condition. And so you could check 32 times 0.68, and we'd also need to check 32 times 1 minus 0.68. And so if you have a calculator, you should be able to calculate that out. And I've got this first one is 21.76. Second one is 10.24, and I didn't actually do that on purpose at all, but it actually just barely satisfies the condition. And so, yes, success-failure condition is satisfied. And so based on our rule, then we'd say that the sampling distribution is approximately normal. The mean of our sampling distribution, it will vary depending on, so it's going to change for each of us. I think mine actually was exactly 0.680, but this isn't always exactly going to be 0.68 because we only took kind of thousands of samples. It would be exactly 0.68 if we kind of took an infinite amount of samples, which is pretty much impossible. So this isn't always exactly 0.68, but it should be close. So I think the first time I did it, I got like 0.676. So the center should be about what the true population proportion is. And then finally, the standard deviation of our sampling distribution. So I wrote that down from earlier. For a sample size of 32, it was 0.081. And so even though we're not deriving the standard deviation formula, we should kind of check to make sure that it's matching up what we got in StatKey. And so if you do this calculation for our example, I got 0.082. And so again, it's not going to match up exactly. So this is kind of the exact answer. This was what we got from taking like 1,000 samples in StatKey. But again, it should be close. Okay. So we'll kind of end it here. This is I know it's a little bit abstract and still kind of theoretical, but in the next video we'll start confidence intervals, which will be a lot more applied, and we'll see how we're using these concepts from sampling distributions when we make confidence intervals.